Okay, good morning. It's a big pleasure to introduce Alberto Abbondandolo from Bochum. I think his first time here was in 2009, right?
At least this is a good upper bound, I think.
Yeah. Yeah.
I also reconstructed this.
Yeah, I think so. Okay, and he will tell us about Birkhoff sections for periodic orbits of minimal action. Sorry.
Okay. So thank you very much. Thank you very much for the invitation. Yeah, I think it was 2009 the first time I came, and yeah, so it's then it came more times, maybe 3 or 4 times to this meeting and also to other meetings at IMPA. But this has somehow been, the important meeting at IMPA, and this is where I first met people who then later became collaborators and friends, Leonardo, Umberto, Pedro. So it's really nice to be here. Okay, so today, everything I'm saying today is joint work with Oliver Ettmeyer, and Jiangsu Kang. Okay, and the setting I will be today is R4 with a standard symplectic form, and we'll be looking at a Hamiltonian H, let's say smooth, and at a regular energy level, let's say sigma, H minus 1 of, let's say 1, regular level. And the important thing throughout the talk will be that sigma today is strictly convex. Maybe strong, maybe a more precise word, let's call it strongly convex. No, but by this I mean, for instance, the second differential of H is positive. It's a level of a positive definite. And of course also compact, I also want, right? Both. Or if you want positive sectional curvature. Okay, and in this, and the other, well, the objects I'm interested today is precisely what Vincent was talking about, namely Birkhoff sections for the Hamiltonian. Now we look at the Hamiltonian flows, and today I'm actually interested in disk-like Birkhoff sections. Okay, to recall, these will be closed embedded disk. So in this case, it's really embedded up to the boundary. Closed embedded disk. So two-dimensional disk whose interior is transverse to the vector field. So the vector field of the Hamiltonian, we'll call it XH. And this should be transverse to the interior of our disk. The boundary of our disk should be a periodic orbit. And then every other orbit, well, just make it with a picture. Every other point will meet the disk both in the future and in the past. Okay, this is the things I'm interested in, and as maybe many of you know, in 1998, Hofer, Vysotsky, and Sender proved an important theorem about existence of such things, namely exactly in this setting, when the hypersurface sigma is strongly convex, the flow admits a disk-like global Birkhoff section. So sigma as above, implies there exists a Birkhoff disk-like Birkhoff section. Okay. And in the same paper, they asked, because the Birkhoff section they found, on the boundary there was a periodic orbit of Conley-Zender index 3. And these are actually, so if you take orbits which minimize action, they also have Conley-Zender index 3. So in some sense it was very natural to ask, this is the question they asked, do periodic orbits with minimal action bound disk-like Birkhoff sections? Okay, and so here, of course, the action, I will denote it with A, the action of an orbit gamma is you integrate, I'll call it d gamma, you take any disk bounded by gamma, now this time in, let's say, in R4 or whatever, and you integrate the omega naught. Okay, this is the action, and under these assumptions, the action is always positive. Of course, you put the right orientation. The action is always strictly positive, and there is always, well, actually a compact set of periodic orbits of minimal action. And one would like to know if those bound a global disk-like Birkhoff section. Maybe before I state the result, let me also discuss this notion a bit. In 2014, Umberto, so Niewicz 2014, first of all, I'm using today always convexity as assumption. The theorem which is proven here, of course, they were in the convex setting, but actually this theorem is proven for dynamically convex, which means that all periodic orbits should have Conley-Zender index at least 3, which was a condition which was actually introduced in this paper, and it's a condition which holds whenever you have strong convexity, but it's more general than that. And in this setting of dynamically convex, so under dynamically convex assumption, Umberto proved that gamma bounds a disk-like Birkhoff section if and only if gamma is a so-called Hopf orbit. Here, a Hopf means the following. Well, first of all, it means it should be unknotted. Well, this, of course, is clear that you need this if you wanted to bound this disk-like. No, because here we notice we are in, this is a curve in a three-dimensional manifold, so it's a knot, and of course it should be unknotted. But then this Hopf condition is a condition which actually also involves the contact structure. You could see it like this. Let's say you have your convex surface. Let's assume that the region which is bounded by this convex surface contains the origin. And then project your system radially on, use the radial map to the standard 3-sphere. Okay? You get your red flow there. And there your flow will be transverse to the standard contact structure. And what you want is that you can find, so this orbit will be what is called a transverse knot. it's transverse to the contact structure. What you want is that you're able to deform this knot while keeping it transverse to the contact structure so that it reaches a fiber of the Hopf vibration, hence the name. Okay, so this is a necessary and sufficient condition for having this disk-like. So in a sense, the condition of having bounding a disk-like global surface of section is something which you can read just from, it's a contact topological condition under this dynamically convex assumption. Okay, this was Reniewicz 2014, and some years before, Heinz 2007, Heinz proved that if, so let's call K1, K2, and K3 the principal curvatures of our surface. Let's order them maybe like this, and they're all positive. And let's assume that there is a pinching condition. So K3 is not too large with respect to the other one, meaning that it's less or equal than K1 plus K2. Under this assumption, he proved that the orbits of minimal action are Hopf. Okay, so if you put these two results together, you deduce that under this pinching assumption on the curvature, the answer to the Hofer-Wysowski-Zender question is yes, they do bound. Okay, and the theorem I would like to discuss today, it's a joint theorem with Oliver and Jiangsu, is that, yeah, the answer is actually it's always yes. So if sigma is strongly convex, then any periodic orbit with minimal action bounds a disk-like Birkhoff section. Okay. Questions about the statement? Okay. Yeah.
Not about the statement, but can you give an example of an orbit that does not bound?
You could take a knot. For instance, yeah. Let's say any transverse. Take any transverse knot type. Okay. Then you can find a Reb flow on S3, which will have this. Actually, you can also, so without this convexity, you can also make that this is the, well, you can have Reb flows where this is a periodic orbit. You can also make this, so this is the orbit with minimal action. Okay, so in general, you can have, yeah. Yeah. An embedded contact homology. I think so, but I would not. Yeah. Okay. Okay. Thanks. Yeah. You put it. You just multiply your contact form by a function which has a minimum along this orbit and then goes up. Yeah. Yeah, yes. If it's just convex, you could look at, well, maybe you start from a bidisk. Let's make it like this. So let's say this is, you look at first the convex set Z in C2, where Z1 squared is maybe a usual thing, less A pi is less than 1, and the same Z2 squared B pi less than 1. Okay, this would be the image in the moment map. Okay, so here you would have orbits with minimal action here. Okay, this is not smooth, but you can smoothen it. And all these orbits here, okay, they are unknotted, but they are somehow parallel, so they do not link with each other. Okay, so such an orbit, if you take any of these orbits, these are all periodic orbits of minimal action, any of those does not bound a disk-like Birkhoff section, because a disk-like Birkhoff section has to link with all other orbits. Okay, so if you remove strict, then this is not true. What would stay true is that among orbits of minimal action, you find unknotted ones. I'm not even sure if, I would guess that they are all unknotted, but this actually, I don't have a proof to show that they are all unknotted, the one with minimal action, if you have just convexity. Yes, if you tilt, well, you destroy the others. One, then you keep only one, and the other one then start, yeah. Yeah. I really don't know. Our proof really uses convexity in a very strong sense, and yeah, I just don't know. More questions? Okay, then maybe I will just state a corollary, but I don't really want to discuss this. A corollary is that in dimension 4, let's say if K now contained in R4, now it's enough to assume that this is a convex body. Now, not strictly convex, maybe let's say also smooth boundary. Then the cylindrical capacity. The cylindrical symplectic capacity is the area of the smallest cylinder in which you can symplectically embed your K. This agrees with, let's call it A min of K, meaning this is the minimum action of orbits on the boundary. Okay? And so in some sense, as you know, there was this question whether all normalized symplectic capacities agree on convex sets. And it was shown that really many of these symplectic capacities coincide with A min, okay? And the ones for which it was absolutely not clear how to show were the extremal symplectic capacity, the smallest one, which is the Gromov width, and the biggest one, which is the cylindrical one. For the Gromov width, it's actually false. There is this counterexample by Patsitaim Kislev and Yaron Ostrover, who showed that the Gromov width can be strictly smaller than this number. So it's not true that all normalized symplectic capacities agree on convex body. However, at least in dimension 4, the largest one does agree. So this brings together that all the intermediate let's say, for instance, all spectral capacities Yeah, that's another reason why all spectral capacities will agree with a mean, and so in particular also the one coming from ACH. And so yes, it's the one seen by ACH. Yeah. Okay, so if you add the axiom of spectrality in the definition of capacity, then it becomes true, at least in dimension 4, that on convex bodies they are all the same. Okay, and this corollary actually follows from a beautiful paper of Oliver, where he uses disk-like surface of section in order to produce symplectic embeddings. So once you have the disk-like surface section, there is an elementary, ingenious but elementary construction which produces the symplectic embedding into the cylinder. Okay. Now I think, yeah, I have half an hour to tell you something about the proof. So in that sense, we start with the approach of Hofer, Vysotsky, and Zender. How does this, which is actually the approach which was introduced, really the whole thing was introduced in this fundamental paper by 1998. So let me add some things then. Now let's assume that the origin, let's say, belongs to the region, the open region bounded by sigma. Then we can also assume H, in this case, maybe let's assume this to be positively 2 homogeneous. Okay, it's the unique function which has the value 1 on the boundary, and then you extend by 2 homogeneity. And then what else? In this case, what we know is that the Hamiltonian vector field then is precisely the Reb vector field of the contact form will be lambda naught. So lambda naught is the standard radial primitive, 1/2 sum j from 1 to 2, pj dqj minus qj dpj. And we take this radial primitive and we restrict it to this sigma. Okay, this is a contact form, and this is precisely its Reb vector field. Okay, and then we also have the contact structure, which will be the kernel of this restriction, lambda naught. Okay, then what Hofer, Vysotsky, and Zender did is they considered a J. This, you start with an almost, well, first of all, we consider the symplectization. So if you want R4 minus the origin, this you can identify it with 0 plus infinity cross sigma, basically using this polar coordinates. So you have coordinates here, and then here the variable r. The variable r is precisely h. Okay, so r equal 1 coincides with sigma, and then you rescale. So this is what's called, this is the symplectization of our contact manifold. It receives. Yeah, and then I want to consider J. Well, I start with an almost complex structure. First of all, on sigma, which should just be, let's say, compatible with orientation. So if I take, so sigma has a canonical orientation. If I take a vector in sigma, this vector v, jv, should be a positively oriented basis. And then, sigma, so J is a complex is an almost complex structure on Xi. Xi, yeah, I said sigma, sorry. Xi, yeah, on Xi. And yes, and then we can extend it to almost complex structure now on well, we want to extend to an almost complex structure on the whole symplectization, and you do it by first saying, I want to map this radial vector to the Reb vector field, and of course then the Reb vector field will be mapped to minus this vector because we want this to be a complex structure, and then you also extend by homogeneity, R homogeneity. You make it translation invariant under this R expansion. Okay, this is what is called symplectization compatible, almost complex structure. Okay, and these things were considered in this setting of dynamics for the first time by Hofer, but before that. And well, why is this almost complex structure interesting? The interest is that if you look now, if now gamma is a T-periodic orbit on sigma, and then you look at this map, U goes from C star, so C minus the origin, to our symplectization, so 0 plus infinity cross sigma, and this should map, so in polar coordinates, R E theta should go, here I want to go to gamma T divided by 2 pi theta, and here what do I put? R to this power, I guess, T to the power 2 pi. You do a small computation, and you see that this is holomorphic. This is J holomorphic. So in other words, yeah, the U composed with I is JU composed with the differential. So the differential of U commutes with or intertwines the almost complex structure J with the complex structure that you have here. So the picture is, let me also make some pictures. We have here our convex, strongly convex surface, and somewhere there is a periodic orbit. Here is the origin. So I'm seeing the symplectization as R4 minus the origin, and then I'm looking at sort of well, it will be a cylinder in symplectization, or if you want, a cone in this R4, which looks like this. Okay, and this cone here is holomorphic. And of course, once you see this thing, it becomes natural to say, okay, let's say then this can become a way to find periodic orbits. Because now I could look, instead of looking for cylinders, I could look, for instance, at geolomorphic planes in this symplectization. And what you expect is, at least if you have some suitable notion of finite energy, what you would expect, since you have these solutions, is that these geolomorphic planes will be asymptotic. So a geolomorphic plane, so now a map from C to the symplectization, still intertwining I and J, you expect it to be asymptotic in this way to periodic orbits, and therefore this can become a way of finding periodic orbits, and this is how Hofer in 1993 proved the Weinstein conjecture for overtwisted S3. Okay, this was 1993, but then together with Vysotskii and Zender, they realized, well, so these things would hold also in higher dimension, but instead in dimension 4, they realized that this can also be used as a way of producing surface of section. The observation is just you would like to take one of these holomorphic planes, now project project it to the surface sigma radially. And here the relevant proposition, which is in Hofer-Vysotskii and Zender. So let's say that U now from C to this symplectization, 0 plus infinity cross sigma. Now it's, well, I should also write it's a finite energy holomorphic plane. I mean, it solves this equation. Well, finite energy will actually be implied what we're writing now. Asymptotic to a periodic orbit gamma. Let's assume that this periodic orbit gamma has Conley-Zender index. In their proposition, they assume less or equal than 3. And then let's also assume that U is an embedding. This is the important thing. Okay, as a map in R4 minus the origin, or in the symplectization, is an embedding. Then, well, I can project, let's call sigma. This is just a projection from in this product space in the symplectization to sigma. I project U on sigma, the image, I take the closure. This is now is a disk-like Birkhoff section. Okay, so you use, actually this information on the index is used to ensure that the thing was embedded in the symplectization, but also when you project, it stays embedded. Okay, and then it will be basically by construction transverse to the flow, and so this is a nice way of producing these Birkhoff sections. Okay, so this means if you want to follow this strategy, our goal is produce embedded, but the important thing is this, embedded holomorphic planes, which are asymptotic to our orbits of minimal action. So in their proof, in the proof of this theorem, they could not, so they could produce these embedded holomorphic planes, but they could not control to which orbits they are asymptotic to. Because, yeah?
Do they really get that it's a Birkhoff section or just a section? How do you prove that in the orbit?
They really, so, well, here the global thing is that there is dynamical convexity, and they really get the whole open book. But the assumption is dynamical convexity overall, otherwise nothing is true. Yeah. Okay, so which means that maybe I can write it like this. So there is a weaker statement, because yeah, if I assume dynamically convex and I assume also this, then maybe I can write it like this. Yeah. Yeah. In their thing there is, but then this actually can be removed. This is also part of the work of Umberto. Exactly. In this thing there is no non-degeneracy assumption. This you can remove, but it requires work. And also in their work, so in their work there is no non-degeneracy assumption. This required some more thing. And then also in this, let's say in this more general thing where of Umberto also there is no non-degeneracy has been removed wherever possible. Okay, so because here the way of producing these planes was, a standard idea in analysis. You start from a problem you can solve. The problem you can solve is when sigma is actually the boundary of an ellipsoid, because there you understand your holomorphic planes, if you choose the right J, and then you start deforming. Actually here the right way is not deform, but do something which is called next stretching. And so from a problem you can solve, you find solutions also of your deformed problem, but in this deformation you lose control. In the ellipsoid, your nice orbit was asymptotic to the ones of minimal action, but after this deformation you lose this information. So this is why a bit the difficulty in this question. Okay, so let's see what is the strategy of our proof. The strategy, I need more space. Okay, let's maybe write here the strategy. I can squeeze it in here probably. So remember, no? Aim is find, aim 0, find embedded holomorphic plane. Asymptotic, of course, to our gamma of minimal action. This is the aim. Step 1 will be turn this aim 0 into a counting problem for holomorphic planes. This will be step 1. Step 2 will be turn and aim, this is now our aim 1, right? Then we want to turn aim 1 into still a counting problem but for Floer cylinders. And then step 3 will be turn aim 2. So instead of counting Floer cylinders, now because here I'm always translating, I start from a problem I cannot solve, I translate into other problems I cannot solve. But then you go on until maybe you find a problem you can solve. You turn aim 2 now into a counting problem. But for gradient flow lines, of the so-called Clark dual action function. And this eventually, this problem 3, counting this gradient flow line, is something we can solve. This is something easy to solve, and then you solve all the way back to the first. Okay, this is the strategy. So in order to explain how this works, let's start with 1. What is this counting problem for planes? Here we just look at our, let's say, planes, let's call it, so let's fix gamma will be this orbit of minimal action. And then I will denote by m gamma, comma j. These are holomorphic planes, u from C to, well, I want to work actually not in the symplectization, but in the completion, meaning I want really to work in the whole R4. So this means that our J will have this symplectization type, but just outside of a neighborhood of the origin. Okay, of course, otherwise you would get a singularity at the origin. So near the origin can be whatever, but outside should be the one we saw before. Okay, because I would like to work here. Okay, I look at these planes which are asymptotic to gamma. And I want to mod out automorphisms of C fixing 0. Okay, in some sense, I'm keeping a marked point on my cylinder. And then on this space, of course, I have an evaluation map from this space to R4, which is just an equivalent class of these maps U. Since my thing I'm just fixing the 0, this is well defined, what is U of 0. Doesn't depend on the thing. So I have this evaluation mapping at the marked point. And what I'm claiming is several things. This M gamma J for generic J is a 4-dimensional, it's a 4-manifold. It's a smooth 4-manifold. And this map Ev is, let's say, or it's orientation preserving at regular points. So whenever it's differential of this evaluation, so this is a 4-dimensional manifold, whenever the differential is an isomorphism, then it's actually an orientation preserving one. Right? This is something that can be proved by standard things. And the other thing is that this is also, well, the evaluation map is proper. Okay, you have enough compactness. If you know that your holomorphic planes pass through a point which is contained in a compact set, then you have enough compactness. This is particularly easy to prove when, since you are assuming that this is the orbit of minimal action, you cannot break because there's no other orbit below that. Okay, so because of that, then it means, maybe I didn't say, it's an oriented. When I say oriented, it means really it comes with a canonical orientation. There is a canonical orientation. This is because, complex linear operators have canonical orientations. Basically comes from that. So it's an oriented for a manifold. And you have this. So then it means that we have a well-defined degree. We have this proper map. We have a well-defined degree, and this degree, of course, will be then greater or equal than 0 because of this condition, and will actually be positive as soon as this thing is non-empty. Let's say positive if... of course, when I say these are manifolds, it's the usual thing. These are manifolds provided they are not empty. Or maybe the empty set is a manifold of any dimension you want, or of any property you want. Okay, and then the first result which meets this reduction is that you have this global, so gamma bounds dislike Birkhoff section if and only if this degree of the evaluation map is 1. Okay, why is this so? Well, why is this so, for instance, for this map, which is in some sense what is more interesting for us? Why, if from the degree 1, can we deduce this? Okay, in other words, from degree 1, we want to apply Hoffer-Wysocki-Zehnder. From degree 1, we want to deduce that the planes are embedded. Okay? But if the planes are not embedded, then they have a self-intersection. Generically, you can assume it's something like this. But now a plane with a self-intersection in this space here counts as you have two different planes where the evaluation map maps to the same point. Right? It's just this. Okay? And since everything counts positively here, this just cannot happen. Okay? So this is the reason behind this thing. Okay? So it means that this is now our new aim. prove that, well, this space is non-empty, and that actually this degree is 1. Questions? Okay. Then let's go to 2. What? So the degree is always greater or equal than 0, and it's strictly positive if and only if it's, sorry, not empty. Yeah, sorry. Yeah. Yeah, or maybe 0 if only if empty. Okay, yeah, thanks. Okay. What is the other thing? Now let's assume that gamma is, let's simplify a bit our thing, is non-degenerate and unique orbit with minimal action. And then up to rescaling, let's assume that the action is 1. In other words, the period is 1. Okay? Then we can compose, I want to modify my Hamiltonian basically to see only this, I want to turn this fixed energy problem as usual in a fixed period problem. And I want to, so this already is an orbit of period 1, but I want to cook up a Hamiltonian which does not have any other non-trivial orbits of period 1. And you do it very easily by you taking some function which does like this. Here at 1 it has slope 1. Here it has slope 1 plus epsilon. Okay, this is the function key. And k is just key composed H. Okay, we don't have any other orbits of action between 1 and 1 plus epsilon, so this means that xk has precisely 2 one-periodic orbits, namely gamma and the origin. Let's call the origin Z naught. At the origin, of course, we have a fixed point, which is a periodic orbit, and then we have gamma. That's it. Okay? And then it turns out, so now we see everything in our 4. We forget about symplectization, and then you can write down we can look at the Floer cylinders going from gamma to Z naught. I will write it in this form. No? These are the U's on R cross T to R4. This is the Floer equation. No, the Floer equation is dSu. I want to write it as positive gradient. So gradient with L2 gradient of the action of U. And I want U at plus infinity to be gamma and U at minus infinity to be Z naught. And then I want to mod out translations. S goes into S plus S naught. Okay? It turns out that this thing here has Conley-Zender index 3, and this has Conley-Zender index 2. Well, to be precise, I should do something more, because this gamma, this is an autonomous Hamiltonian, so this gamma would be like, you have an SOM family of Hamiltonians, so I should put a small perturbation, so this becomes actually a small time-dependent perturbation, so that this becomes 2 orbits, one of Conley index 3 and Conley index 4, but let me ignore all these subtleties not to make too much of a mess. Okay? Index 3, in the index 2, this thing here, this is a nice finite set. Okay? It's a zero-dimensional manifold. It's an oriented zero-dimensional manifold. And but when I'm saying oriented, okay, oriented seems nothing. When I'm saying oriented, I'm meaning here, now there are basically two possible orientations, but only 2. Even if these are many points, the data on the bounds, they produce only 2 possible orientations. So the count of this thing, at least the absolute value of the count of this set, is well defined. Okay? And then the next proposition is that, what is this count? The count, the absolute value of the algebraic number of this. Well, it's an integer, natural number, and not, possibly 0, times the degree of f. Okay? This is the next thing that one can prove. This is proving actually by, looks strange, but by standard methods which was introduced, for instance, Bourgeois and Oancia. You want, in some sense, you start from here, from this Floer equation, somewhere you want to, so in the Floer equation, your Hamiltonian is non-zero. It's nowhere constant if you want, but then you put your Hamiltonian constant in some big region, and then in this region you do you stretch the neck, and then your problem will will deform to more problems. But one of those problems will be actually this counting problem and will appear here. The other problems, okay, we don't care exactly what. We can write exactly what the other problems are, and they have some count, which is this number. Okay? But then the thing is, after we have this was preposition 2, now our next aim, and this is aim 2, is just to show that this count is 1, the count now of Floer cylinders. If we prove that this count is 1, well, then this has to be 1. Okay, this is 1, but k, but we don't care. But in particular, this has to be 1. Okay, so we are just using the fact that this Diophantine equation has only this solution. Okay, so this is what we want to achieve. And here comes now Clark duality, and this is part 3. So in Clark duality, and this we can do it because now this Hamiltonian here is convex. Okay, we can cook up things that this Hamiltonian here is convex. In Clark duality, you have another action function. I'll write it for you. K is still defined on X, is still a loop from R mod Z to R4. So it's a one periodic loop, like in the usual action functional. And this is minus the action of X. Okay, just change the sign. And then instead of writing minus the integral of the Hamiltonian, you write plus. And here you integrate K star. This is the Fenchel dual, Legendre dual Hamiltonian, but in all, not just in the p's, in all variables. Because our K is convex, so you can do the Legendre dual in this vector space. And here you plug in minus, this is the standard J naught on X. And here there is the velocity. And this is an integral on R mod Z. Okay, this is the Clark dual action functional. Notice that this functional is invariant under translations. So we can look at it on, let's say, C infinity. Of course, then you have to use Sobolev spaces to study it. But let's look, we look at C infinity R4 modulo translations in R4. Now, the action is invariant under the translation, and this is also invariant under the translation because here we have the derivative. The other important thing is that now this term, so in the usual action functional, the action dominates over the integral of the Hamiltonian because it's the part with the derivative, and this has no derivative. Here instead, here we have just a, since it's a half derivative because it's integral of x dot times x, morally. So here we are integrating a half derivative, and here we have a full derivative. So this becomes the leading part of the function, and this is convex. So this functional will have critical points with finite Morse index, and it turns out that so critical points of CA, K are in one-to-one correspondence with critical points of the direct. So with AK, I indicate the, well, maybe I should have defined it when I wrote the Floer equation somewhere. Sorry, this was the Floer equation for K. AK is just the symplectic action minus integral of the Hamiltonian. Okay, and here it's just, okay, given a periodic orbit, you just consider its equivalence class modulo translations. And the other way around, for every critical point here, there exists precisely one translation so that this is a critical point here. Not only, but in this one-to-one correspondence, the Morse index, or if you want, the Conley-Zender index of gamma is the Morse index of gamma plus 2. In dimension 2n, it would be plus n. Okay, and once you have this thing, you can look now at this in our situation. In our situation, we have just Z naught, which has now Morse index 0, and you have gamma, which has Morse index now 1, right? Because those were 2 and 3. Now they become 0 and 1. And then you also do another little computation. You prove, okay, this Morse index 0, the functional, it means has a local minimum at Z naught. And then you do a little computation, and you show that the infimum of this function ck is minus infinity. This is true precisely because this slope, we went above the slope where we see the first orbit. Okay? It's very easy to understand how this functional changes when you change the slope. When you change the slope, you get more and more direction in which the function goes to minus infinity. This is the first one where it goes to minus infinity. So it means our function does this, but somewhere it goes to minus infinity. So somewhere it must have a critical point. Okay? And the critical point is precisely, so it means that our gamma is a mountain pass for this functional. And here, what is the count of gradient flow lines here? Well, since the situation is like this, we have precisely one gradient flow line which is going here, and everything else is going down there. Okay? So this is a critical point of index 1. This unstable manifold is one dimension, and due to the mountain pass geometry, we will have precisely one gradient flow line n here. So the last thing that you have to prove, and this is proposition 3, is that the count in Floer homology, so, or if you want, the count of, I will write it without, I didn't say what is, mm of gamma Z naught. This is the count of gradient flow orbits flowing from Z to Z naught. What you have to prove is that this is the same as the count in Floer homology. Because this, we know that it's 1 from this picture. Okay? So the thing is then to prove this, and this requires, now, well, my time is over, so I don't have time to explain you how this goes. Here there is a nice boundary value problem for half Floer cylinders that you can study, and which gives you this correspondence between the Morse homology of the Clark dual functional and the Floer homology of the other function. It's a usual situation in which you have two different functionals which have, however, the same critical points. So you really expect that there is some way to relate in the homologies, and then you look at it sufficiently hard, and you find this way, and then this works, and then you can prove this, which then eventually completes the proof. And yeah, thank you for your attention.